Continuing with Markov chains, we come to a concept, absorbing Markov chains, and let's define that. But first we'll define an absorbing state. A state is called an absorbing state if it's impossible to leave it. What that means, say it's state I, is that on the diagram for the transition you'd see only one arrow going out and coming right back in with probability 1. Or if you took the transition matrix A, then the AII entry would be 1. In other words, from I to, you can only go to I with probability 1. Now, a Markov chain is called absorbing if it satisfies two conditions. First of all, it has to have at least one absorbing state, could be more. And secondly, from every state, it's possible to reach an absorbing state, and not necessarily in one step, but through a chain you could get from any state to an absorbing state. And in an absorbing chain, if a state is not an absorbing state, then it's called a transient state. And now let's take an example. We'll call it the Drunkards Walk. Instead of reading all this, I'll leave it for you to read and I'll show you the diagram. The story talks about blocks and corners. Really the important thing are the corners. I mean, this is block 1, 2, 3, and 4, but it has corners. We'll call the corners 0 and 1, 1 and 2. 0 through 4 are the corners. So I can write the state space 0, 1, 2, 3, 4. And here's the transition diagram. Now, the rule is this. If he's not on one of the end corners, if he's in one of the middle ones, then he'll go either left or right with probability a half each, equal 50-50. From 3 he can go to 2 or 4. From 2 he can go to 3 or to 1. And the difference is at the end corners, one of them is the bar and one of them is home. And if he gets to the bar or home, then he stays there. That's the absorbing state, the two absorbing states. So 0 and 4 are absorbing states. And the others, 1, 2, and 3, are transient. And now what we want to do is get the transition matrix. Here's the transition matrix, and we keep the numbering according to the order here. So this was like state 0, 1, 2, 3, 4, the from state, to state 0, 1, 2, 3, 4. For example, from state 2, I can go to 1 or to 3 with a probability of 50% each. From state 0, I can only go to state 0 with certainty. I put this in a different color to emphasize it. And 4 is also an absorbing state. So from 4, I can only go to 4 with probability 1. Now, for this scenario, this Markov chain, there is no limiting distribution. I can explain why. In the limit, eventually, if he just keeps walking at random, he will reach one of the endpoints, but we don't know which, so it's ambiguous. He'll always reach either 0 or 4 with probability 1. I mean, in principle, he could just keep going back and forth here, but the probability of doing that for infinity is 0. He will eventually reach one of these two, but there's no single limiting distribution. However, there are steady states. The first and last rows, sorry, I wrote columns, I meant to say rows, are steady states. This state where he is home with probability 1 will just perpetuate itself, because 1's an absorbing state. If he's home, then he's home, and he's home, and he's home, then he's home. And if he's in the bar, then he's in the bar, he's in the bar. So those are two steady states. Now, to make the math easier, it's customary to put the transient states before the absorbent states. So we reorder and we get that the state space is 1, 2, 3, and then I've emphasized the comma here, then the 0, 4. Transient before absorbent. And then the transition matrix is said to be in canonical form. And here's the canonical form. The first three states are 1, 2, 3, and the last two are 0, 4. And we see the 1s here on the diagonal. That's because we're going from an absorbing space to an absorbing space. It has to go to itself, so we get 1s here. The 0s here are because we can't go from an absorbing state anywhere. We can't go to a transient state, so these will all be 0s. And as for the rest of it, no special comment, but notice that I've broken it up, I've partitioned it, and we can get a partitioned or block matrix, and then we write A in block form. This part we call Q, this part R, this is just zeros, but it's not a square matrix, and I is an identity of size of however many absorbing states there are. Okay, new page. Going to introduce a few more technical terms. So let's say that the number of absorbent states is R. In our example, R was 2, and T is the number of transient states, and that was 3 in our example. Then Q is a T by T matrix, 3 by 3 we had. I is a 2 by 2 identity matrix. R is a 3 by 2 matrix, and this here is just a matrix of zeros, R by T, which is a 2 rows, 3 columns matrix. Now there are special properties of block matrices in the way you do arithmetic with them. We can show that A to the n is Q to the n, the same 0 and I, and here we don't know what. You know what, I'll illustrate it for A squared. A squared is Q R 0 I won't bother with the lines, times Q R 0 I. Now, it turns out that you can multiply as if they were just like, not matrices, like they were elements.